As always-on AR devices become more common in everyday settings, a key challenge is meeting the privacy needs of multiple people in a fine-grained manner. Consider this hospital setting, where a vision-impaired person is using AR to generate scene descriptions and safely navigate. They pass other visitors and potentially capture sensitive activities, but they might also be subjected to privacy violations from other AR users. To balance the user experience and privacy needs of multiple AR users and bystanders, we explore how to facilitate negotiations of sensing capabilities. This process determines how to adjust AR applications' sensing permissions to align with the interpersonal privacy preferences of co-located individuals, resulting in an allowed set of sensing capabilities for each user. Let's walk through an example. In this ownership-based negotiation, when the vision-impaired user enters a privacy-conscious person's proxemic zone, they are subjected to any sensing restrictions that zone owner sees fit. They may lose access to critical navigation functionality enabled by spatial mapping and people detection. This simple negotiation strategy is part of a broader conceptual framework for achieving a privacy equilibrium, which we instantiate in a simulation toolkit to demonstrate its feasibility. Let's take a look at two other strategies that leverage constrained optimization to achieve a better balance between UX and privacy. In the privacy-first strategy, we optimize negotiations to uphold individuals' privacy preferences, while trying to maintain a minimum level of user experience. This results in some restrictions to speech and people detection, but it preserves spatial mapping, which is the most critical to this user's safety. Conversely, the interaction-first strategy optimizes negotiations to grant required sensing capabilities, while still trying to satisfy interpersonal privacy preferences. In this case, the pink user's privacy threshold was met, so all permissions were granted to the vision-impaired user. We can also establish privacy equilibriums at different scopes, which define the users involved. With the space-wide scope, all users in the same physical environment or subset of the space participate in the sensing negotiation. We saw examples of the zone-wide scope earlier, where each user is allocated a portion of the space, and negotiations occur when users' zones overlap. Finally, we could use a peer-to-peer approach to negotiate between pairs of individuals. This is quite similar to the zone-wide scope, but results in slight differences with chained configurations of 3 or more users. Each of these strategies result in different trade-offs between AR user experience and privacy, which we refer to as equilibrium points, and visualize along the Pareto frontier. To approximate these trade-offs, we compute 2 scores. Permission satisfaction, the weighted sum of each user's required AR sensing capabilities that they are allowed to use, and privacy satisfaction, the weighted sum of each user's interpersonal privacy preferences that other users are in compliance with. Using various thresholds for these scores, our constrained optimization approach produces points with more balanced trade-offs in the middle of the curve. To enable comparing trade-offs across these strategies, our toolkit provides a visualization dashboard. Points on the Pareto frontier represent unique equilibrium points achieved through different negotiation strategies, and the trade-offs across users can be explored in depth through timeline visualizations. The ownership-based strategy resulted in a large UX drop for the blue vision-impaired user, while the privacy-first optimization strategy maintained UX completely. Using different thresholds could result in a more equal compromise for both individuals. To assess the effectiveness of our framework and toolkit, we conducted an application-driven evaluation and toolkit walkthroughs with 8 researchers at the intersection of AR and security and privacy. Together, our findings demonstrated the flexibility of our optimization approach to achieve many possible equilibrium points, and the potential of our framework and toolkit to guide the development of future privacy-mediating techniques for AR.